So today we have work done by a variable force. All right. So our work done by a variable force. We're now going to introduce our calculus into our work here. So real quick review. That work equals F dot delta R, okay, which winds up being our force times our displacement in the direction of the force, and we compensate for that by using a cosine of 90 degrees. Another way of discussing this is that some discuss this as the shadow of the work into the direction of motion. So real quick, we've got a line here and a line here, and then we'll have a vector that's I'm just going to draw the vector. I don't want a line here. Okay, so there's a vector, and our shadow in the x direction would be like that. Okay, and so if we were to shine a light up here, and it would be, okay, so if we were like shine a light above our force vector, it would cast a shadow onto our x direction. That would be that long, and that would be the cosine of that theta. So if this was our force, then this would wind up being force cosine theta right there. And then if our displacement was, if we had, if that was our r, then this direction would be, okay, so whatever the direction, the r direction is, then the shadow would fall onto the r, and that would be our force. So it's a graphic way of explaining it without getting into the math, but if this confuses you, then ignore this and just stick with our formula. Okay, so that's real quick review. However, we're going to simplify this. In fact, I'm even going to erase this drawing. So, voila. Okay, so we're going to start with a pretty simplistic version, a pretty simplistic edition of it. We're going to have a 3 Newton force. Okay, that we're going to apply over a displacement of 5 meters. All right, and we're going to graph it. All right, so here's our graph, and this is going to be our force, and this is going to be our, in this case, we'll just call it x for right now, delta x. Okay, and we're going to have 3 newtons. All right, so we're going to have a 3 Newton force that's going to happen for over 5 meters and 3 newtons, and we can divide all this up, make all these. Oh, my pen is not being very exact right now. Okay, and then we find this spot right in here, okay, creates a rectangle that is this is a rectangle that is 1 Newton tall and 1 meter wide, and this gives us an area, okay, of 1 Newton meter And we know that 1 Newton meter equals 1 joule. Okay, so I'm sure you see where this is going, that we have this totally profound idea in science and math that we can, whenever we have two multiplied values to create a product, or whenever we have a value that is the product of two other values, we can take the area underneath the graphic relationship of those two variables, and that would be the product. That value is the product. So this whole thing right here, okay, this whole value right here is going to be our 3 newtons times our 5 meters, and which will give us, a total number of 15 squares, right? And each square equals 1 joule, and so we equals 15. Equals 15 joules, and that's all happy and fine and dandy, and and right now, the representation of this, okay, mind you, that's cool, okay, and we'd love to waste time by drawing graphs and all looks pretty and stuff, but there's a much easier way of doing this. We have a force times a distance, and we've given this as work equals force times our displacement times cosine of the distance between them. And in this case, it's 0. So the cosine of 0 is 1. So we get, we get our 3 newtons times our 5 meters times 1, and that gives us our 15 joules. That way, okay? Yes, I know my 5 and my J don't look very different. That's because of my pen. It's not because of me. Just saying. All right. So, we can add up our number of squares and we can find the area. And we've done all this before because our quantity that's defined as a product of two other quantities, we can use the area to find that value. Well, that's on that last graph, though. That was our force. That was a constant force over the 5 meters. What if our force varies with its position? So force what if we have a force that's varying with position? So if we have a force varying with our position, there are a number of situations where you've seen this. Have you guys ever seen you guys ever tried to pull a bow? Yes. Like a bow and arrow? Okay. Well, not a compound bow, just a regular bow for starters. Okay, and it's up there and you pull, and the more you pull, the much harder it gets. Okay, the more you pull. Compound bows now, you pull on them, and you have to pull to a particular point, and then once you're there, you can relax a little bit, and all you have to do is release. Okay, or there's a decrease in pressure, or a decrease in force that you have to be exerting, because if you're out there in the woods, you're going to hunt your turkey. Okay, right? And you're hunting for dinner. You don't want to be sitting up in your bow shade, okay, for too long, because your arm will get tired, because you're going to be sitting there out for a long time, waiting for it, waiting. And they go. Okay, and so guys, so the compound bow is made for hunting in particular, so that you don't have to sit in a ready position for so long that your arm tires out. Now, the original bow, the longbow, the British longbow, the archers of the British longbow. If you go look at your military history of the Battle of Agincourt. The British longbows were able to fire their arrows up to 400 yards, okay, with a bow that was about 6.5 feet tall. Okay, and so, and they were able to spread it out with, they were the biggest guy. It wasn't the knights, because the knights had to carry all of their weight on them. So yes, they had to be built, but they also weren't all that big. They weren't huge. The biggest guys in the army were the archers, and they had to have shoulders of these huge wide shoulders and really long arms to get as much stretch on the longbow as possible, and they would just be ripped across their upper body in order to stretch the longbow. Okay, the longer you can stretch the longbow, the more force you can put into it, the more energy you could transfer from your chemical energy into the stored energy in the bow to loose your arrow. And the longer you could fire. So the longbow, which revolutionized warfare, required guys that were really strong, and possibly even stronger than the knights. Let alone the fact that the knights that died because of all the arrows were wearing these huge things of armor that would get pierced by these longbows, but they were stuck in the mud. They couldn't get through. They couldn't get through the land, and they weren't very mobile where the archers were. So that's a long story there, but that's basic idea. I do want you guys right now to assume that force and direction are in the same force. The force and the displacement are in the same direction right now. So we have a variable force. It's going to look something like... That's really ugly. Let's do... That's better. Okay. And how have we done this in the past? We know that our force is going to equal, whatever our... Well, we take this piece by piece. And we had to find the area under this. We divide this into its. We divide it into its little rectangles, right? We divide our rectangles. I wish they were all uniform size, but I don't have the time for that. I do ever have the trick where I can make vertical lines. That's a nice help. Okay, so and we get it. So we have all these rectangles, and we draw the height of the rectangle. The height of the rectangle is, of course, f of x, right? This is f of x. Okay, and this is x in meters. And our f is f of x times our delta x right here, because each one of these itty bitty little guys is delta x, and our height here is f, and so if we take the area of one of these, this whole thing is going to be f of x delta x, and then to find all of them, then we take the sum of all of those rectangles from I equals 0 to n of however many we have, right? And then we want to do the same sum, except as the limit of delta x approaches 0. 0, not theta, 0. And that's just really ugly, so let me try and rewrite that. Okay, so we want 1 to n, and the limit as delta x approaches 0 of this whole summation, and we have learned by now that this whole summation is really the integral. Okay, of our initial x to our final x of our force times our differential x, okay, and this whole thing equals our work if we have a force that varies with displacement. Okay, but this is not yet finished. This will work conceptually, but it's not. We're not being as rigorous as we should. This really converts to that our work equals integral of our radius, our initial position, to our final position of our force vector times our displacement vector. Okay, and we will start with this and then we simplify. Okay. Yeah. And really what happens is, because of the cosine theta part, okay, keep in mind that this right here, that this is a dot product of our force vector times our time to change in displacement. All right. So this is the general form for our work by varying force. The most common one you guys are going to see is given by, it's something we actually haven't lectured on right now, but hopefully you guys picked it up in your book, is work done by a spring. Okay, and so we're going to do a bit of a real quick Hooke's law discussion. So we have a we have a crate, because we always have a crate. We like crates. Crate. Okay, so here's a crate with a little box right here. I think I want this over here a little bit further. All right, and on our crate, our crate is attached to a spring. Okay, our crate has mass M. All right. And we're going to talk about, now it is on wheels. By the way, whenever I put something on wheels, assume that there's no friction. Okay, because the last thing we want to be doing is calculating all of the friction and stuff that's going to be involved with something that's on wheels. That is a colossal pain in the rear, and we're not going to mess with that right now. So no friction here, but we want to do a quick little force diagram on our cart. Okay, so here's our center of mass, which I haven't really introduced. We're just going to do it from a point right here. This is our cart. All right, this point is our cart. Okay, so what forces do we have on this? We have, of course, mg. We've got normal force, but the spring isn't acting in either of those directions, and so there's going to be no work in those directions. We don't have to worry about those guys. But we do have, let's say we stretch this cart. We move this cart a distance delta x. All right, and we'll call this x max. No, Corey, not x lax, x max. Okay, yes, how I can read your mind. Okay, okay. So the maximum distance that is pulled over is our x max. Okay, when we talk about a spring, the distance of a spring, the displacement of the spring is always measured from some equilibrium position 0. All right, so this cart right now, we'll call this spot right here position 0. All right, and so we're either going to have a displacement in this direction, which we'll call positive. Let's draw our, this is positive x in this direction over here. So our x max is going to be positive direction, then we go the other direction, it'll be negative. All right, so our forces are going to be normal and our gravity, and then we also have, there's going to be a retracting force. If we pull our cart, image up here, if we pull our cart this way, there's going to be a retracting force, a restoring force due to the spring that is going to pull in the other direction. This is going to be the force of the spring, F sub S. Okay. All right, and if we were to graph our force, we would have, okay, if we go forward, okay, the force acting on this is going to be negative. So if this out here is our x max, the force at x max is actually going to be negative. It's going to be in the opposite direction to where our opposite direction to our displacement. Okay, we know that there is we know that at zero, if it's not displacement, there is no force acting on it. And if we go all the way out to the x max in the other direction, so at negative x max, okay, then we're going to have our maximum positive force. Well, the work done in the positive x direction is all below zero, right? If this is our force, it's all below zero. So this would all be negative work. That does not show up very well at all, does it? Negative work. Now can you see it? Still no? Poop. All right, let's try this. Negative work. How's that? Yes? Okay. That we can see. Okay. Now we go the other direction. All this is going to be positive work. And that didn't show up well either. Son of a gun. That looks better. Yeah? Okay, so that's going to be positive work if we travel in the negative x direction. All right? So, but you can see here that there's a relationship between our distance and our force, right? And it is linear. And so our work done by the spring, mind you, we're still on, I'm sorry, not our work, our force. Our force done by our spring, okay, is proportional to x, but it's in the opposite direction to it, and it is given by a constant, aided by a constant k, and this k is called the spring constant. Okay, it is in units of newtons per meter. And so how many newtons is the force for every meter that you extend or compress the spring? All right. Okay, and those are both vectors. So the spring constant is given in newtons per meter, and it is a measurement of the stiffness of the spring. The greater the spring constant, the more difficult it is to extend or compress. Okay, really high examples of really high spring constant springs are those in like semi-truck suspensions. Okay, you can see you can like look under a truck and you'll see these massive coils underneath, and those have really high spring constants. Some really low ones. Slinky is notoriously low. Okay. It is, however, a spring, and it is great for certain demonstrations, but it's a way low spring constant. we've got some in here. We'll mess with some. I think tomorrow or maybe the next day is going to be like a lab day. We're going to take some time off and mess with some of our goodies over here, and to give you guys time to study for your test. Right, so that's the spring constant. Now, the work done by this, the work done by our spring is going to equal the integral of our initial position, minus our final x position, final x position, not our final x position, of f of x dx. But our f of x equals negative kx. So we plug this in here, and this is pretty simplistic right now. Our work is going to equal, and if we just go from equilibrium position out to x max, it's going to be 0 to whatever that x is, negative kx dx. Right, so if we evaluate that, this becomes negative k x squared over 2 from 0 to x. All right, we keep evaluating because it's a definite integral, so we get negative kx squared over 2 minus 0. And so we wind up with the work equals negative 1/2 k x squared, and this is the work done by a spring. Now, interesting thing here. I'm going to draw this in a little box down here because it's sort of an aside. All right. All right. So to sort of an aside, if we do this, if we take this integral from that negative x max to the positive x max, of our kx dx negative over here, then we get negative kx squared over 2 from negative x max to positive x max. And we evaluate it, this winds up being negative kx squared over 2 minus a negative kx squared over 2, which winds up being 0. And whenever we have this concept where the work, as we go from one position to another position, on either sides of some 0 point, this is a conservative force. And we will get to more of this next week with our law of conservation of energy. But when we have a force, that will give you a force that does 0 work over a particular distance, over a set of displacements, it is considered a conservative force. And some examples of that are gravity, springs, pretty much anything that you would have an equilibrium around becomes a conservative force. That is right. So in other words, so if no work is done when you finish where you start, right? You go out and you come back and there's no work done. That's our conservative force. That is it for our variable work, and